We can smooth a signal by convolving it with a rectangular function. This process averages the signal over a small interval, reducing sharp changes. Here, r epsilon of t is a rectangular function of width epsilon and height 1 over epsilon. The output signal h of t is the convolution of the input signal f with the rectangular function r epsilon. The convolution simplifies to this integral, which averages f over the interval from t minus epsilon to t. As epsilon approaches 0, the difference quotient becomes the derivative of f, which is just f of t. Thus, in the limit, the smoothed signal returns to the original signal. A Dirac delta, denoted delta of t, is a generalized function or distribution. It is defined by two key properties. First, delta of t is 0 everywhere except at t equals 0, where it is infinite. Second, the integral of delta times any continuous function f gives the value of f at 0. From these properties, it follows that the integral of delta over all t is 1. Convolving any signal f with the Dirac delta returns the original signal. This is because the delta function samples the signal at a single point. Let's see how convolution with the Dirac delta works for a specific function. By definition, the convolution is the integral of f of s times delta of t minus s. Using the sifting property of the delta function, the result is simply f evaluated at t. For our example, this gives t squared.